Hey class, this is Mr. Roberts at Shasta High School. Glad you're here. We're going to be looking at solving literal equations today. Literal equations. And it sounds weird when I say that. So it's like, oh really, equations? Yeah, literal ones. What I mean by literal equations is that we're going to have equations that have multiple variables in them. So not just a single variable, but multiple ones. And the idea is to solve it for one of the variables in the list. So this first one says that I would like you to solve the equation 3a equals c for a. I want to get a alone. And there's properties of equalities that we can use. Property of equalities are things like the fact that if I have two things that are equal to each other and I divide both sides by something that's equal to itself, I get another equation that's equivalent to the one I have. So when I look at this, I could definitely take the left-hand side and divide by 3, and I could also take the right-hand side and divide that by 3. And when I do that, when I divide both the left-hand side and the right-hand side by 3, over on the left-hand side I end up with this 3 over 3. So that's a giant 1, and this literally just becomes a is equal to c over 3. So 1/3 c, or c divided by 3, is what a is. So that is an example of solving a literal equation. I solved for a. Let's look at another one. Here's another one. I'd like you to solve this one for b. Okay, so when I look at it, I can see that there's again two sides of the equation, and I want to get b alone. I want this by itself. Well, I can see that b is being increased by this 3a, right? And it's a positive 3a. It's being increased by b. So what I can do is I can take away 3a from both sides. So I can literally write 3a plus b. That's what I had before. And I'm going to, oops, I didn't want to do that. I want to, there we go. I want to take away a 3a from that side. And on the other side of the equation, I've got f, and I'm going to take away 3a from that side also. So what happens is when we look at it, you can see that there's a positive 3a on the left-hand side and a negative 3a. Those two combine to make 0. So what I'm left with on the left-hand side is just plain old b, and b will equal f minus 3a. So there we go. I've solved that equation for b. b is now by itself. b is equal to f minus 3a. Let's look at another example. Actually, let's do the same one, but instead of solving for b, let's this time solve it for a. So this time, right, you can see over here I've got this variable a. Oh, where'd my pen go? There it is. I've got this variable a, and I want to get it alone this time instead of b. So what I'm going to do is I'm going to take away 3a from each side first. So that's going to, I'm going to take away b from each side. So that's going to give me 3a, and then I'll write it. It's a plus b and then a minus b from that side. And over on the right-hand side, I've got an f, and I'm going to subtract a b also. Again, big picture, look at it. I had things that were equal, and I took away b from both sides. If you have equal things and you take away equal things, you get equal things. So I know that this equation is equivalent to the original equation. It can be simplified for sure. This is just the same as 3a is f minus b, right? 3 times a is f minus b. And then the final thing I could do is I can divide both sides by 3. And I can show it two ways, right? I can divide the left-hand side by 3, and that would give me just a. But if I take the right-hand side and divide it by 3, I can get f minus b the whole side over 3. Or I can recognize that's the same as me taking each term there and dividing each one by 3. So I can also write that that's a is equal to f over 3 minus b over 3. The important thing that I see is that every single term on both the left and the right-hand side is being divided by 3. Or I can even make it look like it's being multiplied by 1/3. So I can also write a is equal to 1/3 of f minus 1/3 of b. And those are all equivalent to each other, right? All three of these say exactly the same thing. So in this equation, I've gotten a alone, and we've solved each one of those for a in terms of f and b. Let's move down to another equation. This one says solve for y, and this looks like we're going to have a pretty easy time doing this, right? Because what I'm going to do is I'm just going to take away, I'm going to add 3 to each side. If I add 3 to the left-hand side, it becomes simply y. And if I add 3 to the right-hand side, I'm just going to write what the right-hand side was, 2 times the quantity of x plus 4. And then I've got plus a 3. And if I want to, I can rewrite this using the distributive property and collecting like terms. Although this is a fine answer, if it depends on what my purpose is. I'm going to go ahead and change this. I'm going to write this is y is equal to 2x plus 8 plus 3. And this 8 plus 3 is 11, so I can also write it as y is equal to 2x plus 11. So what's interesting about that is we now have 2 different ways of writing this linear equation, and I actually want to graph both of those so we can look at them side by side. Oh, it's recording again, right? I hope it is. I hope it is. Yeah, it is. So what I've done is I've copied the equations above me, right? The top one is the one that I originally started with, and the one below that is what I got when I solved for y and got it alone. What I want to do is just demonstrate that these really are the same equation. So I'm going to come in here, I'm going to type y minus, let me get that cursor out of there, y minus 3 is equal to 2 times the quantity of x plus 4, and I can see there's the 1 relationship. And that should be exactly the same as y is equal to 2x plus 11. And I can see, yeah, they totally are the same. In fact, if I click off the green one and back on, you can see that they are totally lining up exactly, showing me and demonstrating to me that these are indeed equivalent equations. They're saying the same thing. Y minus 3 times 2 times the quantity of x plus 4 is the same thing as y equals 2x plus 11. So when you use these properties of equality, you get equations that are equivalent to the other ones. Let's move on to another problem. Actually, let's take a look at this one again, but this time let's solve it for x, right? So we did just solve for y. Now I want to take it, and instead of solving for y, I want to get x alone. So to do that, I'm going to use the distributive property first. I'll just rewrite the y minus 3, and then rewriting the right-hand side, that's going to become 2x plus 8. Now, I'm going to subtract 8 from both sides, right? It's a plus 8, so I'm going to take away 8. So that's going to become y minus 11 is equal to 2x. Okay. Now I'm going to divide everything by 2. So that means that I could say y over 2, or I could say 1/2 of what y is minus 1/2 of 11, or I'll say 11/2 is what x is. Okay, so I have x alone here. X is 1/2 y minus 11/2. Okay, so I guess sometimes if we're trying to solve for one of our variables, we may have to help liberate that variable by using the distributive property first, and then we can proceed from there. So that's an example of rewriting the equation. Let's move on. This is a formula, right? This is a formula for the area of a triangle. The area of a triangle is 1/2 times the base times the height. And here, we could be in a situation where we know what the area is and we know what the base is, and the question is, hey, what would we know the area and we know the height, and the question would be, what's the base, right? What's the base? So we may need to take an equation like this and solve it for b. So if I wanted to do this solve for b, the first thing I'm noticing is that there's a fraction there, which I'm not a huge fan of. So I'm going to go ahead and multiply both sides of this equation by the number 2. And I can see there's only one term on each side, right? I don't see any addition or subtraction, so I've got a term of a on the left-hand side and a term of 1/2 times bh on the right-hand side, so just a single term on each side. When I multiply by 2, I get 2 times a equals b times h. Okay, you see what I've done? 2a equals bh. Now, because I'm trying to get b alone, again, I want to get b alone, I'm just going to divide both sides by h. When I divide the right-hand side by h, it's going to give me just b, right? In other words, my thinking is if I have b times h over h, right, this is a giant 1 and I'm left with just b. And over on the right-hand side, I would have 2 times a, and all of that is divided by h. So I've done it. I've solved for the base. The base is twice the area of the triangle divided by the height. Who knew? I didn't. I kind of did. But again, this is just another example of solving a literal equation, getting one of the variables alone in terms of the other. So we're going to look at something that's a little bit related to this, and it's another way to write down the equation of a line. So we know that if we're given 2 points, we can come up with the equation of the line in slope-intercept form. This is kind of another way to do that without going through the whole process of solving for b, solving for the y-intercept. So just a quick example. Let's say that we have a slope. I'll say our slope, and I'll use m for it, is 2/3. And let's say that we also have this point. We're going to say we have the point 6, 10. Okay, so we know a point and we know the slope. We know our point contains both an x value and our point contains a y value. So this is the point slope form. Watch how I write it down and listen to how I say it. The point slope form is always y minus the value of y that you know. So I wrote y sub 1. So y, the variable, minus the y that you know equals the slope times the quantity of x minus the x value that you know. So this, right, is the equation of a line, and I can literally just go from the slope and point and write this down and create the line that would have this slope of 2/3 and hit the point 610. And it would look like this: y minus the y value that I know, which is 10, equals my slope, which is 2/3, times the quantity of x minus the x value that I know, which is the number 6. So there we go, perfectly. That's it. And in fact, if I graph this, and we will do that, I'll see this line completely. But also, let's solve for y, right? I can add 10 to both sides, and I can also distribute this 2/3 to both the x, and I can distribute the 2/3 to the -6. So if I do this distributive property first, I get 2/3 of x, and then -6 divided by 3 is -2, times 2 would be a -4, and then over here I've got y minus 10. And then to get y alone, I'm going to add 10 to both sides. So if I add 10 to the left-hand side, I have just y, right? Y minus 10 plus 10 is just y. And over on the right-hand side, I'm going to have 2/3 of x. I've got a -4 plus 10. -4 plus 10 is +6. So what we're going to see is that when we graph this first bracket and we graph this second bracket, these equations will be exactly the same. And in fact, let me drag those. I think I can just drag these. Yeah, I can put it up there, but they're hard to see, aren't they? Well, I can see it at least. Let me drag this one. Drag this one. No, drag this whole thing. Close enough. I'll just put it right there. That'll be enough so I'll be able to see what I'm looking at. So let's go ahead and jump back over to Desmos and look at that. So in the one equation, oh, you can't see all that, but it was y is equal to 2/3 and then times x plus 6, right? That's the point slope form. But the one that I just wrote down, right, and I didn't solve for b, I just wrote this down, was y minus the y value that I know, right, y minus 10, oops, y minus 10 equals 2/3 times the quantity of x, whoops, x minus the x value that I know. And you can see, sure enough, as soon as I do that, I end up getting the same line twice. It's right there, right, purple, and then the other one is black. So those two lines are exactly the same. Let me put them back. I don't like, there we go. So there we are. They're exactly the same. Y minus 10 equals 2/3 times the quantity of x minus 6 is the exact same line as y equals 2/3 x plus 6. All right, let's look at a couple more point slope forms. So let's say that I give you an equation where you have this slope of 2/3 and you have the point of 5,7. Okay, remember when I give you a point that contains both an x value and a y value, and these are the x and y values that we know. So for reference, I'm going to write this down because I'm trying to practice it. It's y minus the y value that I know equals my slope number times the quantity of x minus the x value that I know. So my y, that value that I knew was 7, so I could write y minus 7 equals my slope, which is 2/3 times x minus the x value that I know. There we go. There we go. That is the equation of this line. If I graphed it, I guarantee you that this line would go through 5,7 and it would hit the point 2/3. That sounds like quite a claim. Let's verify that claim. So I'll plug this back up here. Boy, my memory is not great. I just lost track of that. Y minus 7. Okay, so we're going to go y minus 7. Y minus 7 equals, it was 2/3 times, 2/3 times the quantity of x minus, x minus what? X minus 5. X minus 5, put it in the parentheses, 5. So the thing that I care about are two things. Does this indeed hit the point 5,7? So let's look at it. Does it go through 5,7? Well, here x is 5, and look at that, right? I can hit it, I can click my cursor and I can move right here and I can see clearly when x is 5, y is 7, so it's definitely hitting it. And the other thing, it has to have a slope pattern of up to over 3. So let's see. I know it's hitting here, so I can go up 2 and then over 1, 2, and 3. Excellent. Clearly up 2 over 3 is the correct. So I could go down 2 and back 3, and this would be another nice point with integer coefficients. And then the next one would be over here, right, at -1, 3, I think it is. Yep, -1, 3. All right, so there we go. It hit exactly where it should. One last example we're going to look at is, let's say that you're given 2 points rather. And I don't know why I put this. I'm given a point. I'm not given a slope. I'm given a point, and I'm given another point. So I'm given a point and another point. What's the equation of the line that goes through that? Well, the first thing I am going to need is I am going to need the slope. So I'll just remind myself that the slope is how much y values change divided by how much x values change. And I can see right here, this is a y and this is a y. So I can say, look, I'm just going to take the 7 and subtract 5. So I took the bottom y and subtract the one above it. And then below that, I'm going to do my change in my x's. So I'm going to take my 5 and subtract 1. So in my numerator, I have 2. In my denominator, I have 4. So it looks like I have a slope of 1/2. So that's my slope. Now, with this point slope thing, right, I don't have to solve for b. I can literally just write it down. So again, I'm practicing it, so I keep saying it. Y minus the y value that I know equals my slope times x minus the x value that I know. And I'm showing the ones that I know with these subscripts. It doesn't matter which one of these points I use. I'm going to go ahead and use the first one. It's got both an x and a y. So now I can say y minus the y that I know, which is going to be 5. So y minus 5 equals my slope, which is 1/2, times the quantity x minus the x value that I know. There you go. That equation is going to hit 2 points. It's going to hit 5,7. And you know, that is definitely worth looking at. So let me grab this, and I'm going to copy and paste it so it's here. And then I'm going to ask this thing to turn this into a nice, beautiful equation. There we go. Good job. The other thing I want to do is, I think I want to make the font. Can I make it let's see, let's change the color of that. I think I can make it, yes, and bold. You can't see it, but if I drag it over here above, oh, there we go. It's above, wait, get it back over there. If I drove it up above my face, you can see that one. So what we're going to do now is we're going to graph this, and we're going to make sure that it really hits these 2 points, because I have the correct solution if it goes through 1, 5, and 5, 7. If it doesn't hit those, I've messed up. So to verify that, let's bring back up Desmos. I'll clear that. Let me bring this over a little bit more. And I'm just going to go ahead and graph y minus 5 equals 1/2 times the quantity of x minus 1. And as soon as I press enter and I look at it, what I'm trying to see is, does this hit 2 points? Does it hit 1, 5, and does it hit 5, 7? So let's see. I guess I could ask it this way. I can say, is 1, 5 on there? Well, sure it is, right? And if I wanted, I could actually graph it. I can go 1, 5. It's there. Clearly it's a point. And the other point was 5, 7, and I can see it. There it is, right? So to highlight it, I'll just go 5, 7. Whoops, not and 7, 5, 7. There we go. So I definitely have the equation of the line that goes through the 2 given points. So that's something you're going to be practicing today and tomorrow. How do you find the equation of a line where you're given 2 points? How do you find the equation of the line where you're given a slope and a point? But I want you to write these in point-slope form, which is actually easier than what we've done in the past. So you're going to be practicing writing these in point-slope form. Hey guys, I hope you have a great day. Look forward to seeing you on Class in Line again soon. This is Mr. Robert. I'll talk to you later.